Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 2. We will present about our foundation analysis, and our company names is PL Constructions. So our team consists 6 members, which are Nur Husna Muslim, Nur Shafia Ismail, Nur Fatima binti Helmi, Nur Hana Shaila binti Asman, Nur Atira Iliani binti Rani, Siti Aisyah binti Abdul Rahim. My name is Nur Fatima binti Helmi. So I'll present for the introduction, objective, and also result of shallow foundation. So for introduction, it is crucial to apply geotechnical and foundation engineering competence to conduct a foundation analysis. The design foundation of structure require the knowledge as follows. As you can see from this slide, there are 4 knowledge, which is the load that will transfer from the superstructure to the foundation system. Second one, regional construction code, behavior and stress related to property of the soil that will support the foundation system. And the last one is geological characteristic of the soil under examination. So our project is about a 4-story apartment. So the objective is to support the feasibility of the project's shallow and deep foundation designs. Number 2, to define the site project's design concern, bearing capacity, and settlement. And the last objective is to determine whether soil improvement measures are necessary for foundation building.
Hi, my name is Siti Aisyah binti Abdul Rahim. My metric number is DF2086. I'm going to continue with the soil analysis. Standard Penetration Test (SPT) is an in-situ dynamic penetration test designed to provide information on the geotechnical engineering properties of soil, and this project is analyzed based on SPT. From the borehole data, we may obtain the sample result and the number of blows, which is N value. Continue with the equation of N60 and N160 to get the angle of internal friction. So here we calculate the value of each depth at the table and get the average angle of friction for this test, which is 36 degrees. This is the result from the bore log data that contain the characteristic and the description of the soil. The water level of the soil is at 5.8 meter below the ground level. Here is the soil profile for the borehole. There are also the density of the soil and water at each depth. Next, we continue to the column load. So this is the load at every column computed by Esteem software. For design foundation, the critical load from column is only considered in this design to obtain the appropriate design. A total number of 7 columns was used in this project. For grouping of column load, here is the maximum load that each group can support. The load is divided into 3 groups. Group 1 is for ultimate axial load below 900 kN. Group 2 is in the range of 900 to 1000, and Group 3 is for ultimate axial load above 900 kN.
Okay, this slide shows the result for shallow foundation. So there are requirements that we use to design shallow foundation. So for the depth, we propose 1.5 meter, and the gamma is result, so it will be 14.59 kilonewton per meter cubic. And since the degree is 36 degrees, so we got NQ 13.97 and NY 9.41. So the safe bearing capacity is 150 kilonewton per meter square because it's sandy soil. And the equation is 0, again because of the sandy soil. So from the square foundation formula Terzaghi, we can simplify the formula is QU equal to Q and Q plus 0.4 gamma B and gamma. So the result for group 1, the load from column for group 1, the maximum is 838. So we got B 2.5 meter, Q 21.89 kilonewton per meter square, QU 444.09 kilonewton per meter square, Q ultimate 2769.31 kilonewton, and the Q allowable is 923.10 kilonewton. So since the applied load is smaller than allowable, so we can justify that the design is satisfied. Same goes for group 2 and group 3. As you can see from this slide, from group 2, the applied from the column load is 958, and the allowable load is gross allowable load is 1103.41. So the design is satisfied. And also for group 3, the applied load is 1343, smaller than 106,043.66. So this design is also satisfied for all group. Okay, that's all from me. Thank you.
Hi, my name is Norhana Syara binti Azman with metric number DF20148, and I will explain about the settlement analysis. So, for the shallow foundation, we use the method of Berland and Burbidge, which is for the group 1, which is with the load is 838 kilonewton. The first step is we need to find the depth stress influence with the formula given below, which is Z prime. We put the value of BR equal to reference width, which is 0.3 meter, and our width foundation, which is B, equal to 2.50, and the Z prime that we got is 2.06. After that, we need to find the elastic settlement by using the formula given as below. So for this study, it is a normally consolidated sand. So with the L is equal to 2.50 meter, and the alpha 1 is 0.14, and the alpha 2 by using the formula given is 1.71 over N60 to the power of 1.4. N60 that we use is 10. And for alpha 3 is equal to 1, and the Q prime is equal to Q net. So the value is 112.20 kilonewton per meter square. And for the atmospheric pressure, which is PA, is equal to 100 kilonewton per meter square. And the final result for the SE is equal to 16 millimeter. And for the group 2, with the load is 958 kilonewton, the depth stress influence Z prime is 2.18, and for the elastic settlement SE, we got 17 millimeter. And the last one, for the shallow foundation group 3, with the load is 1343 kilonewton, the depth stress influence Z prime is 2.48, and for the elastic settlement SE is 17 millimeters.
Assalamualaikum warahmatullahi wabarakatuh. My name is Noor Atiraidani Binturani, and my matrix number is TF200149. I will present about the deep foundation calculation, which is we assume that the value of L and the cross section is similar for the three loads. For example, for L, we choose 24 meter, and for the cross section is 0.7 meter times 0.7 meter. To calculate the deep foundation, we need to find the QP and QS. For the QP, we use three methods, which are Meyerhof method, basic method, cost and Castello method. For the QS, we just use one method only. After calculate the QP for the Meyerhof method, we got two QP, which are 19,693.41 kilonewton and 2,1990.45 kilonewton. So for the QP for Meyerhof method, we choose the smallest one, which is 2,990.45 kilonewton. For the basic method, we use M equal 250, which is the medium sand, and for the N sigma, we got 74.16 from the interpolation. QP for basic method, we got 11,718.71 kilonewton. For Coyle's and Castell's method, we got NQ is 168 and our QP is 19,693.41 kilonewton. And then we calculate the QS. For the L over D is 34, and we got the K is 1.3. It is from the figure 9.17. for the QS, we got two values, which are 5,748.23 kilonewton, and the second one is 2,956.79 kilonewton. And after that, we got the average of QS. Lastly, we need to find the QL for QP and QS. So QP plus QS over FS is equal 3,899.33 kilonewton. And for all the loads that we have, it is a pass. So it is all okay for the L is equal 24 and the cross section is 0.7 meter.
And moving on to the deep foundation, here is the value that we will be used to put in the equation as stated here to find the settlement for the deep foundation. So for the length, we use 24 meter, and for the cross section of the foundation is 0.70 multiplied to 0.70, and for the EP is 21 multiplied to 10 to the power of 6 kilonewton per m2, and for the ES 25,000 kilonewton per m square, and for the distribution is a 0.50, and for the Poisson ratio we use 0.27, and for the IWP is 0.85, and for the IWS, which is by the formula, which is 2 plus 0.35 multiplied to the square root of L over D. And then for the Q all, yeah, which is L over Q, here is a 3,899.33 kilonewton, and for the QWP is 996.82 kilonewton, and for the QWS is 1,916.08 kilonewton. And we put all the information given in here into the each equation for the SE1, SE2, and the SE3. And for the SE1, we got 5.0 millimeter, and for the SE2, we got 45 millimeter, and for the SE3, we got 3 millimeters. And then all of this we will adding to find the total SE, which is the final result is 53 millimeters for the deep foundation settlement.
Assalamualaikum warahmatullahi wabarakatuh. My name is Shafina binti Ismail, matric number DF200116. I will present part design and justification. This is a summary table for shallow foundations. So first of all, our group choose Tagazi's, Meyerhoff, Basic, and Coily and Castello method to calculate these both foundation, deep and shallow. The factor of safety we assume for the project is 3. Our group choose 3 columns to design for each group, which is C6, C5, and C3. Based on the result, it shows that as long as value for Q allowable greater than applied as a load, the design for both shallow and pile foundation is adequate to withstand the applied load. As a result, the structure is deemed safe in this project. So result for settlement is in range 16 to 17 mm. So according to Tagazi's theory, it states that settlement of a shallow foundation is restricted to 25 mm only. So maximum for this project, maximum settlement is 17 mm. So this shallow foundation design is adequate to hold the superstructure above the soil. Move to deep foundations. We can see the result shows that QS is smaller than QP. This is happened due to the soil conditions. So the skin's resistance cannot have a great influence on transferring the load to the soil. Results for settlement for deep foundation for every group is 55 mm. This is due to the flat soil level. So the increase in the number of piles able to distribute the load transfer from the superstructure to the soil. However, in increase in the number of piles, it will increase the size of the pile cap, so the settlement of the pile group cannot be reduced. Therefore, the pile must be sufficient to bear the load applied from superstructure and pile cap. So as a result, for this deep foundation calculation, it is accepted. So to justify this design, the deep foundations is appropriate to use in this undertaking, even though both shallow and deep foundations can withstand the applied axial load.
Assalamualaikum and hi, my name is Nurhusna binti Muslim. My metric number is TF200147. I will present about soil improvement in construction, discussion and conclusion. There are 4 improvements of soil in construction that have been encompassed in this study. The first one is soil improvement without the usage of admixture. There are 3 techniques. The first one is soil removal and replacement. This technique is far more affordable and simpler than deep foundation. Secondly, preloading or pre-compression method. This approach is more profitable for soils that are typically or likely over-consolidated, and it allows the consolidation settling process to be finished quicker. Thirdly, vertical drains. Vertical drains is divided into 2 categories. The first one is sand drains and the second one is weak drains. For sand drains causes a rapid rise in the rate of consolidation, while weak drains effective for expediting the predicted consolidation settling. The second one is soil improvement method by soil densification. There are 5 techniques under this method. Firstly, stone columns or granular piles. This technique improves the bearing capacity of shallow foundations on soft soil while also lowering soil consolidation settling. Secondly, soil cement piles. This approach is primarily used to decrease the consolidation settling of a shallow foundation and to boost the bearing capacity and shear strength of the soil. Thirdly, dynamic compaction. This technique can densify the soil and improve its shearing strength and bearing capacity. Next, jet grouting. This approach boosts soil shear strength by reinforcing the soil with cement columns and lowering consolidation settling before erecting the structure. And the last one is lime piles. This approach has a considerable impact on reducing the expansive soil's expansion potential. The next method is soil reinforcement by geotextile. The geotextile is available in strips or as geogrids to support the soil. And the last one is soil reinforcement with cement, lime, and fly ash. This approach is based on enhancing the binding between soil particles using cement, lime, and fly ash. The addition of lime to clay soil may raise its unconfined shear strength. The cement most likely has a favorable influence on the shear strength of the soil, and the application of fly ash enhances the soil in terms of shear strength. For discussion, the maximum bearing capacity obtained for shallow and deep foundation is 1,643.66 kN and 3,899.33 kN respectively. For deep foundation, the methods used for determining bearing capacity are Meyerhof, Vesic, and Coyle and Castello method. For settlement checking, the method used is Berlin and Burbidge method. In conclusion, deep foundation is decided to be used since the bearing capacity of deep foundation is greater than shallow foundation. Therefore, the objectives of the study have been achieved. That's all from us. Thank you.